Hi, my dear students. I am Sunira from Department of Physics, Government College, Madhya. This is our third lecture in electrodynamics of the book Introduction to Electrodynamics by Griffiths. This is part of part of third semester BSc Physics course of University of Calicut. In our previous lectures, we learnt about vectors and its components form. To discuss component form, we studied about Cartesian coordinate system and right-handed coordinate system. Now, we can extend the study to triple product of vectors. In our previous lecture, we learned about cross product. I think all of you remember all that things. You learned that portion. The cross product, the output of the cross product is a vector. Okay, so we can again we can do operations on this cross product because its result is a vector. So again you can take dot product or cross product with this output of cross product. Isn't it? Then it is called triple product. Okay, for example, suppose we have three vectors, vector A, vector B and vector C. Okay, we have three vectors. In these three vectors, suppose we consider the cross product B cross C. Okay, so this B cross C gives you another vector, right? What about this B cross C? This B cross C represents the area of a parallelogram. Am I right? Okay. B cross C represents the area of a parallelogram. Okay. So, this vector, this B cross C is a vector. This vector is operate with vector A. It have two options. Either it can operate in dot product way or in cross product manner. Okay, so we can think about first the dot product. Dot product. Okay, dot product. This results in scalar triple product. Scalar triple product. Okay, scalar triple product. Because here you can define this as A dot B cross C. So B cross C is a vector. Now we take dot product with A. A dot B cross C. This is called scalar triple product. Okay. What is meaning of this A dot B cross C? This represents geometrical meaning of this. A dot B cross C represents volume of a parallel paper. Volume of parallel pipe. So here vector B and vector C form a parallelogram. Okay, so B cross C, modulus of B cross C, modulus of B cross C represents area of this parallelogram, right? This represents area. Area of this parallelogram spanned by vector B and vector C. Okay. Now, this vector B cross C is a vector. Its modulus is the area of the parallelogram spanned by vector B and vector C. Okay. Now we have a third vector, vector A, orienting along like this. These three vectors form a cubic structure, parallelepiped. given by A dot B cross C. Because from the figure itself, you can see that from this figure itself, you can see that this A cos theta is along this L cap direction or its altitude. Okay, so A dot B cross C gives you volume of the parallel pipe. Okay, so scalar triple product represents volume of a parallel pipe. That is the geometrical meaning of this scalar triple product. Now, how can we find out this scalar triple product? A dot B cross C. In our previous lecture, we learned that we can find out B cross C using determinant, right? Here also, we can use the determinant form to find out the scalar triple product. Okay, so this A dot B cross C is given by determinant of Ax, Ay, Az, Bx, By, Bz, Cx, Cy, Cz. Right? From where we get this Ax, Ay, Az, etc. All these are the three components of vector A. These are the three components of vector B using Cartesian coordinate system. In our previous lecture we learned about it. So vector B in this Cartesian coordinate system, the three components of vector B is given by Bx, By and Bz. Similarly, vector C is given by Cx, Cy and Cz. Okay, so this determinant gives us the box product. This is called box product. So this scalar triple product is also known as box product. Okay, now we can check its properties. For example, this in the case of box product or scalar triple product, this dot and cross are interchangeable. For example, this A dot B cross C is equal to A cross B dot C. Okay, here the dot and cross product are interchanged. Along with it, the brackets also interchange. Otherwise, there is no meaning. Okay, so A dot B cross C is equal to A cross B dot C. Similarly, we can make this a cyclic change to these vectors, alphabetical order. That also gives you the same vector, same resultant vector. For example, in this case, C cross A dot B. This is also equivalent. All these three are same vector. A dot B cross C equal to A cross B dot C. That's equal to C cross A dot B. If we change this alphabetical order, vector change its direction also. You already learned about it. In the case of cross product, this cross product, if you change the order of the cross product, the resultant vector reverse its direction. Okay, that is valid here also. So, if you keep the alphabetical order, you get the same vector. Otherwise, opposite sign. Resultant vector with the opposite sign. For example, in this case, if you find A dot C cross B, A dot C cross B, this gives you minus A dot B cross C. Okay? Remember these things. Okay, so if you do alphabetical order or cyclic change in this box product or scalar triple product, it gives you same result. But if you change its order or non-alphabetical order, then this gives you an opposite vector, a resultant vector with an opposite sign. Okay, these are the main points connected with this box product or scalar triple product. Now we can move on to the second case, vector triple product. This equation is called vector triple product because the B cross C, the resultant of this vector B cross C is a vector. The vector cross product with vector A cross resultant of vector B cross C. Okay, this represents a vector triple product. This is called vector triple product. Why it is called vector triple product? Because in this case the resultant is a vector. In our previous case the resultant is a scalar. Right? In the case of box product, the resultant is a scalar quantity. We found that it's geometrically equivalent to the volume of a parallelepiped. At the same time, in this case, in the case of vector triple product, the resultant itself is a vector. Okay, so this is a cross product also. So this is not associative. We already learned about cross product. Cross products are not associative. So A cross B cross C is not equal to A cross B cross C. Okay, these two are different vectors because cross product is not associative. Okay, remember this thing. Another property, we can simplify this expression A cross B cross C equal to B times A dot C minus C times A dot B. Okay. This is called back cab rule. We can prove this expression by using the component form of this vector A, vector B and vector C. If you write all these in component form and find out this vector triple product, you can rearrange them like this. Back cab rule. Okay? So, vector A cross vector B cross C gives you back and cab, BAC. B times A dot C minus C times A dot B. Okay? Remember, this resultant of this is a vector. So, if you expand this is also a vector. This term is a scalar, but this scalar is multiplied with this vector. Okay? So, overall, this gives you a vector quantity. Okay? You can further simplify. How, if there are so many cross products in an equation, you can simplify all these expressions into an equation which includes only one cross product using these types of rules. Okay? There is another rule. A cross B dot C cross D. This is equal to A dot C times B dot D minus A dot D times B dot C. Okay, here this resultant of this operation is a scalar quantity because cross product gives you here a vector, this cross product gives you here a vector, then you take dot product among them. So the resultant is a scalar. If you expand like this, the resultant is also a scalar because A dot C is a scalar quantity, B dot D is another scalar quantity. Similarly here also. Okay, so equation which have only one cross product. Okay, so please remember all these things about multiple products of vectors, either scalar products or vector products. Now we can apply all these concepts about the vectors in the case of position, displacement and separation vectors. These vectors are required for our further analysis in this electrodynamics paper. Okay, for that, first of all, what is a position vector? Position vector. So, if you want to locate a point in a three-dimensional space, what we do? We use some coordinate system. For example, our familiar system, suppose Cartesian coordinate system. We can use the Cartesian coordinate system to represent the position of a point in a three-dimensional space. So, consider a coordinate system like this. Cartesian coordinate system, right-hand coordinate system. Okay, in this system, this YZ plane, this board is in the YZ plane and x-axis pointing outward from this board. Okay, now suppose we have to represent a point P. This point is also not on the board, it is somewhere here. Okay, so you can locate this point P using the three coordinates x, y and z. Right? If this point is in the board, you can represent this keeping 0 by z because x coordinate is 0. If this point is not in the board, it is somewhere here, you have all these coordinates x, y and z. Right? Now, using the origin, this is the origin of the coordinate system. You can represent the position of this point P with respect to the origin of the coordinate system using a vector. Okay, so we have a coordinate system, Cartesian coordinate system here with its origin here. Okay, but where is the location of this point origin? 0, 0, 0. All the coordinates are 0 here. Okay, so origin means 0, 0, 0. From this origin, we can draw a vector to the position, to the point P. This vector is called position vector P. Okay, this vector is called position vector. Usually we use the vector R to represent the position vector. Okay, so the point P is the location of the point P is represented by using the position vector from the origin O to the point P. Okay, so now you can write this vector. What's the vector R? Position vector R. Because we already locate the point P is at x, y, z. Okay, so x cap plus y cap plus z cap. X cap is the unit vector along x direction, y cap is along y direction, z cap is along z direction. Okay, so this is the position vector of the point P. What about its modulus? Modulus of this position vector, let it be R. What about this R? This is equal to root of x square plus y square plus z square. Okay. Now what about unit vector? Unit vector along this direction. Unit vector along the position vector. How we can get it? Let it be R cap. This R cap equal to vector R by modulus of vector R. Okay. This is equal to, what is vector? We can get it from here. X cap plus y cap plus z cap divided by root of x square plus y square position vector. This is its magnitude or modulus. This is the unit vector along the position vector R. Okay, so we learned basic things about a position vector. If you want to describe a point in a three-dimensional space, you can use position vector to locate the point there. Okay, now we can think about displacement vector. What is a displacement vector? Suppose we have a point xyz. After a later time, this point is displaced to another point. Let it be P prime. Okay, so initially the point is at P is at x, y, z. Okay, after a later time, P is at x plus dx, y plus dy, z plus dz. Right? Okay. So the point P is initially at xyz. We write the position vectors also. But after a later time, this x changes to x plus dx, y to y plus dy, and z to z plus dz. Now what happened? The point P is displaced through the space. Okay? So we can define a displacement vector. Okay? We can use the notation dl. Okay? This dl equal to dx x cap plus dy y cap plus dz z cap. Okay, this is called displacement vector. This vector is called displacement vector. If this change is very small, it is called infinitesimal displacement vector. Okay, if this change dx, dy and dz are very small change, the vector is called infinitesimal displacement vector. Okay, so we have position vector, then displacement vector. For small variations in coordinates, we call it as infinitesimal displacement vector. Okay, now if you want to write its modulus, it's also possible. You know that how to write modulus. Mod dl equal to root of dx square plus dy square plus dz square. If you need its unit vector, how can you do? Divide this vector with this modulus. Okay, so all these are about this displacement vector. Now we can discuss about separation vector. For that, consider the same coordinate system that we have discussed earlier. Now I just show you the origin of the coordinate system, just to simplify the diagram. Okay. Now I have a source number here. Some point, let it be a charge or something like that. The source is there. So there is a position vector from this origin point to the source point. Okay. This is called source point. Some type of source, a charge or a current source, anything like that, placed in this point. Okay. So I can draw a position vector like this. So vector drawn to the source point from the origin is usually represented using prime coordinates, r prime. Okay. Now suppose I want to find out the effect of this source point some other point. If this is the charge, then I need electric field at some other point. Okay. So suppose this is the point. I want to find out the effect of this source at this point. Okay. If this is charge, I want to find out electric field at this point. Okay. So now I need another position vector to locate this point. Right. So from the origin O, I draw a position vector to the point. This is called right? So r prime is a position vector, r is also another position vector, but this script r is not a position vector. It is called a separation vector. Why? We can just apply vector addition here. From this diagram you can see that vector r prime plus script r gives you vector r, right? Vector r. Okay, vector r prime plus script r gives vector r. Okay, so what is script r? Script r equal to vector r minus r prime. So this is called separation vector because this vector is difference between these two vectors, vector r and vector r prime. Okay, so we can write its magnitude. The magnitude of this separation vector, this is equal to script r. What is magnitude? Magnitude of this vector r minus vector r prime. Okay, now using our Cartesian coordinate system, we can write r prime all things, right? So vector r equal to we can assume let vector r equal to x cap plus y cap plus z cap. Okay, similarly r prime equal to x cap plus y cap plus z cap. Okay, now what we need? We need separation vector. So script vector r equal to r minus r prime. That means x minus x prime x cap plus y minus y prime y cap plus z minus z prime z cap. Right? So the separation vector script r is obtained like this. So what about its modulus? Modulus script r equal to root of what's inside? Yes, x minus x prime square plus y minus y prime square plus z minus z prime square. Okay, x minus x prime square plus y minus y prime square plus z minus z prime square. Okay, now what about the unit vector, separation vector? Script r cap equal to script r divided by modulus of script r. Okay, so now you can substitute here. I am not doing now. You can write vector r and divide with this. This gives you the unit vector along the separation vector. So here we learned about three vectors which we need throughout in this paper electrodynamics. The first one is position vector, next one is displacement vector, the third one is separation vector. Okay, so for that we use source point and field point. Position vectors always start from the origin of the coordinate system. At the same time, this separation vector is in between the source point and the field point. Okay, this script vector is not a position vector, but it is a separation vector. It separates two position vectors. Okay, difference between position vector of source point, difference between the position vector of field point and the position vector of source point. Okay, this gives you the separation vector. I think you clear all these concepts very well. Now we can discuss about transformation of vectors. So we already learned about vectors and we told that there are three components in a vector. And sometimes we use brackets to represent this x, y, z, etc. like that. Okay. A group of mangoes, oranges and bananas. Okay. So we have fruits, right? All of you are happy because you have no mangoes, oranges and bananas, right? All these three fruits are in different baskets. This is NM mangoes, NO oranges and NB bananas, right? All these are fruits. Okay? Fruits. The question is whether these three fruits forms a vector, because in this case the fruits have three components, right? A mango component, orange component and banana component. So these three components form a vector. What you feel? So we can check it whether this happens in the case of vector. What happens to the case of vector? As all of you know, vectors have direction, right? Here there is no direction for the fruits. So if you transform one to another, there is some other rule in the case of vectors. In the case of fruits, there are three components but there is no direction. Okay. So this is not looks like a vector. Since the vectors have three components along with its direction, this is something different from these groups of fruits. Okay. So we can transform one vector in a specific coordinate system to another coordinate system to check how it behaves. Okay. So we can consider a Cartesian coordinate system, right-handed Cartesian coordinate system x, y, z. Here the board is in the yz plane and x-axis pointing outward from this board. Consider a vector A in yz plane. This vector A makes an angle theta with the y-axis. Okay, so we can write vector A equal to ay y cap plus az z cap. Okay, what is ay? Component of A along y direction. What is ay? Ay equal to a cos theta. Similarly, az component of A along z direction. Az equal to a sin theta. Okay, so vector A is equal to a cos theta y cap plus a sin theta z cap. Okay, so we represent a vector A in a Cartesian coordinate system x, y, z like this. Now we want to know how these components transform. So we have to change our frame of reference or coordinate frame. So suppose for simplicity, a simple case, we can analyze a simple case. Suppose I rotate the coordinate system about the x-axis. You know that x-axis points along this direction. So I rotate this coordinate system counterclockwise, like this, counterclockwise, with respect to x-axis through an angle phi. Okay, through an angle phi. So I am representing the new coordinate frame. Okay, so here The new frame is represented by bar. So after rotation through an angle phi, y-axis changed to the position y bar and z-axis changed to a position z bar. What about x-axis? X is equal to x bar because I rotate above the x-axis. Okay, I rotate the coordinate system above the x-axis through an angle phi. So there is no change in x coordinate, x equal to x bar, but the y bar and z bar changed by an angle to an angle phi, counterclockwise direction. Okay. Now I want to represent my vector A in this new coordinate system, x bar, y bar and z bar. You got the point? Initially we have xyz coordinate system, we represent the vector like this. Now I change the coordinate system, just change the frame by rotating phi angle counterclockwise above x-axis. The new frame is x bar, y bar and z bar. Okay, so I want to write this vector A in this new coordinate system. Okay, so vector A in the new coordinate system is ay bar, y bar cap plus az bar, z bar cap. Okay, ay bar, y bar cap plus az bar, z bar cap. Now, what is this ay bar? Ay bar, component of A along y bar direction. So, what is this angle? This angle is theta minus phi. Okay, this angle is theta minus phi. Okay, so ay bar equal to A cos theta minus phi. Okay, similarly az bar equal to A sin theta minus phi. Okay, so you can expand this term. What about cos A minus B? Cos A cos B plus sin A sin B, right? So I can expand it here. So here A cos theta cos phi plus sin theta sin phi. What about this term? In this case, A sin theta cos phi minus cos theta sin phi. Okay, these are the new components of vector A. So you can simplify this equation further. So I can write here, I think. Okay, so ay bar equal to A cos theta cos phi. What is A cos theta? We already find it. A cos theta represents ay, right? A cos theta represents ay. So ay cos phi, right? Plus, what about A sin theta? A sin theta represents az. So az, this term is phi, sin theta sin phi. Okay, az sin phi. Okay, az sin phi. Now coming to, this is a subscript to that, right? Az sin phi. Now coming to the second part, az bar. Az bar equal to A sin theta. A sin theta is az. Az cos phi minus A cos theta. A cos theta is ay AY bar and AZ bar. So what is the relation between these two? Here you can see that AY bar, AZ bar. That's what I write here. AY bar, AZ bar. This is equal to something into AY, AZ. What is here? Cos phi, sin phi. Right? Cos phi, sin phi. Then minus sin phi, cos phi. Okay, so the vector in the XYZ reference frame or XYZ coordinate system transformed into new coordinate system AY bar, AZ bar through this operation, through this transformation. Okay, so here this rule, this is the property of a vector. This transformation rule is obeyed by a vector. So what about our initial example? We discussed about fruits. In the case of mangoes, apples and bananas. If you want to, never you can convert a apple or mango to banana or orange to mango. But here you can convert AY to AY bar. Similarly, AZ to vector AY, AZ to AY bar, AZ bar. So these kinds of rules are obeyed by vectors. This law is called transformation law for a vector. We can generalize this operation. Here this matrix represents the coordinate rotation, counterclockwise coordinate rotation through an angle phi. We can generalize this expression. So we can write here vector A bar, AI bar. Okay. Vector AI bar equal to sigma ij rij aj. Okay. Here vector AI equal to sigma ij rij aj. Okay. Sigma, not sigma ij, sigma j. Sigma j rij aj. This sigma j equal to 1 to 3. What it means? J equal to 1 represent x. J equal to 2 represent y. J equal to 3 represent z. Okay. So you can represent a transformation rule for a vector, general vector in this form. Okay. Or you can write a general expression for a vector in the form of AX bar, AY bar, AZ bar equal to RXX, RXY, RXZ, RYX, RYY, RYZ, RZX, RZY, RZZ into AX, AY, AZ. Right? This is the general transformation rule. The same rule can be written like this. Okay? Here, vector is called a tensor of rank 1. A vector transformed like this. This is the property of a vector. So, vectors has magnitude and direction. Along with it, it obeys the transformation rule. If the coordinate frame changes, the vector obeys the transformation rule like this. Okay, so we can wind up our discussion here. In this lecture, we learned about triple products, including scalar triple product and vector triple product and their geometrical meaning. Then we move on to position vector, displacement vector and separation vector, and finally coming to vector transformations. And found out that vectors obey a particular transformation rule. That means any vector respect to x-axis through an angle phi in a counter-clockwise direction. Hope that all of you understand what we learned